Alright, and this is I'll be showing how to evaluate limits using the idea of asymptotic behavior. So let's start off with one of the limits that we already know, fairly common in any calculus class, and it is the limit as x approaches 0 of sine of x over x. So normally we would go ahead and either use L'Hopital's rule, or we could do it using the geometric version, or using the Taylor series, but we're not going to do that here. What we're going to say is we have to look at the function sine of x. And if we look at its graph, we would see something like this, since it is periodic. But let's just notice that at x approaches 0, we have this small portion right here. And we see that it behaves like x for very small values of x. So we could say that our function sine of x is asymptotic to x. And this doesn't say that for every value of x is true, so we have to make a restriction. So we could say that for every small value like negative 0.1 and 0.1, we get a good approximation of sine of x for very small values of x. It's simply just going to be asymptotic to x itself. And so we see that it is at 0, we could just say, okay, since 0 falls between our interval, negative 0.1 and 0.1, we could say that our limit as x approaches 0 is then going to be x over x, which we know is just 1. And the limit of 1 as x approaches anything is just 1. So we pretty much used this asymptotic relationship to be able to express our limit as just x over x. And this only works for small values of x. And if you were also given like the limit of 0.01, it falls between this interval, so you could go ahead and say, okay, let's just use the asymptotic behavior of sine of x at 0.01. So it's fairly straightforward. Another example is the limit as x approaches 0 of e to the x times cosecant of x. We could go ahead and use the standard methods that we already are being taught in a standard calculus class, but there is a quick shortcut to evaluating this limit, and that is also looking at the cosecant function. So we know that cosecant of x pretty much has behavior that looks like this, or something that looks similar to this. And we know that at 0, it goes towards infinity. So if x equals 0, if you look at it from the right side, then it goes up to positive infinity. And we know that 1 over x, as we look at it from the right side of 0, it is going to be equal to infinity as well. So we could say that cosecant of x is asymptotic to 1 over x for values from 0 and an extremely small number, 0.001. We could just say that that is our interval because they behave nearly the same and they go towards infinity. So since we're evaluating our limit at x equals 0, we could just replace cosecant with 1 over x, as cosecant is exactly asymptotic to 1 over x at x equals 0. So then that becomes the limit as x approaches 0 from the right side, because we're looking at cosecant of 0 from the right side where it shoots off towards positive infinity by going up. So then we have e to the x times 1 over x, which then we see that the x's are going to cancel out, just leaving e. And the limit of e as x approaches anything from any side is going to be e. So our original limit is e. So it's just a matter of being able to determine whether a function is asymptotic to a function that could make our process of evaluating limits easier. And another one we could look at is, let's say, the limit as x approaches 0 of 1 minus cosine of x over, let's say, x squared. So how would we evaluate this limit to be exact? So how would we evaluate this limit? Well, it's a bit tricky, but we have to also look at 1 minus cosine of x. So we look at 1 minus cosine of x. And if we look at its graph and say, okay, so our cosine function is negative, and it is shifted up 1. So what we're going to see is that we have a function that looks something like this. Let me just color it. It is going to look something like this. So a rough sketch like that. And what we're going to look at mainly is simply just this parabolic-like shape. And this pretty much is also going to tell us that 1 minus cosine of x is basically some function of, let's just say, the yellow portion right here is something x squared. And since pretty much it's a bit more difficult to evaluate this function and say it's asymptotic to something, we could say that is x squared over 2, because if we just have x squared and plug in some values for x, we're going to get not close values, but if we simply divide it by 2, we're going to get some close values for cosine, or 1 minus cosine of x. So by that definition, we could say that 1 minus cosine of x is asymptotic to x squared over 2. And if we plug that in for our limit, so we have the limit as x approaches 0 of 1 minus cosine of x, we could replace that with x squared over 2 since it is at 0 exactly where we want to find the limit. So it is going to be x squared over 2x squared. And here we see that the x squares are going to cancel out, which just leaves 1/2. So our original limit is 1/2. And we could also confirm this by using L'Hopital's rule. And by doing that, we have the limit as x approaches 0, and differentiating the top, we simply are left with 0 minus the derivative of cosine, which is positive sine. And then differentiating x squared, we get 2x. And if we bring the 2 out, so it's 1/2 times the limit, we know that this limit from earlier was just 1. So then our limit is, by definition, 1/2. So it's fairly a good thing to understand and know a bit of asymptotic functions. And we also look at this behavior when we look at limits for infinity. Like we could say x cubed plus 5x plus 7 over 2x cubed minus x plus 10. And we know that for big values of x, the x cubed term is going to dominate. So you can pretty much say that all of this, our function f of x, is pretty much asymptotic to x cubed. So our numerator and denominator is just going to be asymptotic to x cubed, because x cubed plus 5x plus 7 is asymptotic to x cubed, as x approaches infinity. And the same could be said for 2x cubed minus x plus 10, which is asymptotic to x cubed for values that approach infinity. So then we're going to have the limit as x approaches infinity of x cubed over, and since x cubed is multiplied by 2, we have to include that 2 because it is a part of the growth. So it is 2x cubed. And we're going to cancel out the x cubed, which is going to give us 1/2. So that means that our original limit is 1/2. And we can also verify this by just using or dividing everything by x cubed. So we're going to have 1 over, or actually 1 plus 5 over x squared plus 7 over x cubed over 2 minus 1 over x squared plus 10 over x cubed. And we know that division by infinity is just 0, so everything's going to cancel out, which just leaves 1/2. So it's just always nice to know that we could look at function and relate them to another function for certain values of x. And for the final problem, we're going to look at a bit of a tricky one. And we're going to look at the limit as x approaches 0 of tan of x minus x over x cubed. And we always want to look at the function that is the hardest to express. And if we look at tan of x, and if we simply look at it just from its first portion, what we have that looks like this. If we just look at this small region of tangent, we see that it behaves cubically, meaning that we could express our tangent function as something cubed. And this helps us understand that we could also relate our tangent function, because for values around 0, it behaves asymptotically to x. But that is not going to be enough. So you have to include another term, because if we substitute tan of x minus x, we're going to get 0, which isn't going to be a very good answer for us to get. And since our expression here is pretty much behaving asymptotically for tangent of x, if we look at just this portion, it is going to be added to x cubed over 3. And you could also get this from the Taylor series of tangent of x, because it's what you would get for either, or for the Taylor series pretty much for that function. So we could say that tan of x is asymptotic to x plus x cubed over 3. So we can now just plug this in, because we're looking at small values of 0. So we could plug that into tangent, and we're going to get the limit as x approaches 0 of x plus x cubed over 3 minus x over x cubed. So the x's are going to cancel out, and the x cubed will as well, just leaving 1/3. So pretty much that means that our original limit is going to equal to 1/3. So it's always a good idea to know when to use asymptotic behavior. And we can also always check our work by using various methods of evaluating limits using logarithmic differentiation, or pretty much being able to express our entire limit as a function of a series, more or less. So that's pretty much it. That's pretty much going to be it for this video, and hopefully you understood a bit of evaluating limits with asymptotic behavior. And yeah, hope you learn from this, and yeah, have a good day.